welcome to my presentation. My name is Mohammad Azami, and I'm a PhD researcher at Concordia University's Aerospace Robotics Lab in Montreal, Canada. Today, I'll be presenting our research on in-space manufacturing, developing lunar infrastructures with robotic additive manufacturing and in-situ resource utilization. Okay. The presentation has two parts. The first part is about a brief overview of an extensive review paper conducted by our team. And it's recently published in Progress in Aerospace Sciences Journal. You can scan the QR code to access the review paper. And the second part of the presentation is about our contribution by developing lunar infrastructure with robotic additive manufacturing and in-situ resource utilization. So what is the motivation, challenges, and possibilities for lunar-based construction and manufacturing? Humanity is preparing to return to the moon with the Artemis missions. And Artemis paves the way for habitation and utilization in space. Manned missions require substantial installations for long-term survival, and LBMC is a necessity for habitation and utilization beyond Earth. As you may know, material and equipment delivery costs can exceed $10,000 per pound, which can make the project uneconomical. So there are two solutions for it. For the material selection, in-situ resource utilization, ISRU, through using lunar soil or lunar regolith, is a solution. And another solution is to do recycling and repurposing. 100% of the material should be recycled. And large-scale fabrication for printing is another solution. We can use small mobile robots that are preferred over printing using a large gantry. Challenges imposed by the lunar environment. Vacuum environment, which imposes outgassing requirements. And low gravity impact. Not all of the additive manufacturing techniques are applicable to the lunar environment. And energy constraints, we have two main energy sources on the moon. The first one is the small nuclear reactors, and the second energy source is solar energy. Extreme temperature fluctuations. As you know, during a lunar day, temperature of the lunar surface fluctuates between minus 130 degrees to temperatures above 120 degrees Celsius. And high material equipment delivery costs that I already discussed in the previous slide. So for LBMC, just like other techniques, other applications, we can the manufacturing techniques can be broadly divided into traditional techniques and additive manufacturing techniques. Traditional techniques offer faster fabrication for simpler geometries, especially in construction. And we can use them for making, for example, regolith-based bricks or landing pads. And additive manufacturing techniques offer flexible on-demand fabrication of complex and customized parts with minimal material wastage. And they are preferred for 3D printed shelters or parts. Traditional techniques are bulk or subtractive, while additive manufacturing techniques are conducted on a layer-by-layer basis. And recent research trends in both academia and space agencies show a growing preference for additive manufacturing over traditional techniques. About the traditional techniques, they still remain relevant because of their proven reliability. An example is regolith casting. It involves heating regolith to a molten state for casting into molds. And fabricating glass and glass fibers through rapid cooling is possible through this technique. Regolith sintering that involves heating regolith to form a solid compact material. Regolith concrete utilizes lunar regolith in construction material. And calcium aluminate, sulfur, or geopolymer concretes are some examples of lunar regolith concrete. Regolith binder is another technique which involves combining regolith with a thermoset or thermoplastic. And ultra-low binder contents from 2 to 5% is achievable through compression molding, which is a big save in the material delivery cost. About additive manufacturing techniques, this slide has some information, brief information, and assessments about powder bed fusion and directed energy deposition techniques for printing lunar regolith. They all offer high to very high maximum percentage of regolith achievable, which is favorable, but WAM is not, WAM needs a metallic matrix. But for energy consumption, they all need moderate to high energy levels, except for solar sintering and microwave sintering, powder bed fusion techniques. And current challenges include, advantages include high precision for laser and EB techniques, but low optical absorption for laser, and less effective for non-metals for electron beam. Solar sintering and microwave sintering are energy efficient, but we have difficulties in process control and resolution. WAM is ideal for fast fabrication of large parts, but it needs a metallic matrix, and the electric arc use is not feasible in a vacuum. Stereolithography apparatus and also binder jetting. These techniques can achieve high to a very high precision, and they offer multi-material printing, and printability of complex shapes is one of the features of these techniques, but they can achieve medium maximum percentage of regolith, and energy consumption is low to moderate for these techniques, unless they need a debinding sintering step. And current challenges for these techniques include recycling issues for the binder, and outgassing and boiling freezing, which are issues related to the ink or polymer used in these techniques. About MEX techniques, material extrusion techniques, triple F and FGF, DIW, direct ink writing. FGF is fused granulate fabrication, and contour crafting, CC. They can achieve medium to high maximum percentage of regolith, and their energy consumption is low, but for EMR, which is extrusion of molten soil, molten regolith, molten lunar regolith, it needs very high energy levels, but it offers a maximum, 100% usability of regolith in this technique. And current advantages for triple F include simplicity and cost effectiveness, but it gives us a layered structure. FGF eliminates filament making step, which is very important for lunar surface to keep it simpler. But it's less. It offers less control compared to triple F. EMR is 100% ISRU based, and the molten regolith can be provided from oxygen extraction processes, and it's hard to control. It's the downside. DIW offers high customization ability and high precision, but again, we have recycling and binder related challenges. And for contour crafting, construction speed is very high, and water evaporation is the main challenge. So now the second part of the presentation about our contribution. PEAK is the polymer binder selected for our research because it's a widely used space-grade polymer. It's polyether ether ketone, and it's 3D printable. It can withstand in high temperatures, high working temperatures of around 250 degrees. And tensile strength is very high compared to many polymers, around 100 megapascals, and low density, and it meets NASA's outgassing requirements. And it offers high radiation and chemical resistance. It's widely used in the space industry, so there's a potential for PEEK to be easier to access and repurpose compared to other polymers, hopefully in future. But synthesizing PEEK in the lunar environment is currently infeasible because there is no big resources of carbon on the lunar environment. So we can address that by incorporating regolith into PEEK as a filler to save costs. We don't have access to big quantities of, big volumes of PEEK, regolith delivered from the moon. So some simulants are developed. We selected Exolith Labs LMS1D Lunar Mare dust because it has finer particles compared to other simulants. And the developed methodology includes processing PEEK and regolith into filament using a twin screw extruder, and then using a high temperature printer, printing the fabrication. The nozzle temperature is around 430 degrees. Ambient temperature is 120 degrees, and bed temperature is 180 degrees. And we do simultaneous annealing during the process. And post-processing annealing is the next step. These are samples printed using PEEK and regolith from pure PEEK to 50%. That is the maximum percentage of regolith that we achieved so far. And the tensile strength curves, PEEK stands on top in terms of ultimate strength, but as we add more regolith particles, we reduce the mechanical performance, but it's not huge, up to 40%. But for 50%, there's a drastic change and decrease in the mechanical strength. Also, as expected, as we add more solid material to the composite, the more we reduce the maximum elongation that it can achieve, it can reach. And for the stiffness is increasing by adding regolith particles, but for 50%, it's decreasing again because of defects that are imposed by high melt viscosity of the composite, which makes the extruding more challenging. Micrography of the samples for PEEK, pure PEEK, we see the layer by layer gaps, interlayer gaps that exist, but with inclusion of regolith particles, the interlayer gaps are almost removed. But for 40%, these are for 40% B and C, and D and E are for 50% regolith and PEEK. We see large defects for 50%, and nanoscale regolith particles can be seen in both pictures. And we see no agglomeration of regolith particles. It's what we were expecting from the particle size distribution analysis. So it proves that the extrusion and melting and mixing strategy is effective. Energy dispersive spectroscopy EDS maps of the composite. This is the areas that we have carbon, which shows the presence of the matrix. And for the particles, as proved, there are non-homogeneous combination of various silicon and metallic oxides. We have silicon, aluminum, titanium, magnesium, iron, and other metals in the structure. Notable findings include incorporation of 50%, which means reducing cost by half, and we can achieve higher, but our equipment is not capable of that for now. And post-processing annealing had no noticeable effect on the tensile process properties due to the simultaneous annealing during the printing. And nozzle temperature significantly impacts the strength. Tensile strength increases from 67 megapascals to 94 megapascals by increasing the nozzle temperature by 10 degrees for peak and lunar regolith, 30%. And adding regolith eliminates significant delamination between the layers of pure peak and reduces warpage as well. And raft material matters for this printing. For peak, we had more than 50% print failure, but for PEC raft, as it offers excellent adhesion to the peak, we can achieve almost 100% print success. Yeah. And tensile strength drops drastically from 40% to 50% due to the print defects likely caused by high melt viscosity, not agglomeration. And this is another contribution by our lab about the robotics aspect. SLAAM is a promising approach for mobile 3D printing, in which large-scale parts are printed in segments. The localization is conducted through simultaneous localization and additive manufacturing, which works based on extended Kalman filters, simultaneous localization, and mapping. And the overall geometric compliance of the part is maintained during the printing process, and sub-millimeter dimensional accuracy is proven on large looping objects. And local and global localization sensor fusion is essential for the precision, and it's capable of printing high temperature polymers and composites like what we developed. And this is a video of robot working. It starts with landmark initialization. First print is conducted. Then the 3D scanner scans the printed part and the robot moves to the new pose for the next print. Total station system observes the landmarks from the new pose. 3D scanners scans the printed part from the new pose and generates point cloud to compare with the previous one. And the next print is conducted. And the process continues until the whole geometry is printed. So this 3D scanned image shows demonstrates that the sub-millimeter dimensional accuracy is achieved on this object of 46 millimeter in length. And future works includes 100% ISRU-based additive manufacturing through powder bed fusion, DED and extrusion of molten regolith. SLAAM can integrate with WAM for large-scale metal printing, and simulations are currently ongoing for the process and the composite. Thanks a lot, and please feel free to ask questions.
Thank you, Mohammed. Any questions from the audience? Because I have a couple. Oh.
Thank you. Nice presentation. I have a question. Have you tried the mixing of peak and with the regolith? You have used LMS. Have you also used LHS or the Highland Simulants, for example?
So that's an interesting question. That can be a very good future work. Not yet, but definitely it's worth trying.
And do you expect that something would change in the tensile strength if you use another simulant?
So definitely we will have some changes in the characteristics, but as we print the binder here, I think it's the most important thing. And this method that we developed is not highly dependent on the regolith concentration. I mean, on the regolith composition, but it's mostly dependent on the regolith particle size distribution. I believe so, but yeah, we need to try it.
Okay, nice. Thank you very much.
Thank you very much. My pleasure.
Thank you.
Thank you for the presentation. A great job. I have a question from the practical point of view. So imagine, okay, so you got the best formulation by adding peak to regolith, right? So and then you optimize the different processes. At the end of the road, so you want to do this on the lunar surface, right?
Yes.
So could you please explain a little bit on that part? Because, for example, you're going to ship peak to, just over the moon, and then how you're going to mix, how you're going to print, right? So a little bit, just explain on that part, please. Yeah.
Yes, that's a very good question as well. So, because of the challenging lunar environment, we definitely face the challenges on the moon. Not all the equipments that we currently have are able to be used on the lunar surface, but it's a, it's an idea demonstration that is feasible, and the next step can be do it on a challenging environment that simulates the lunar environment. But this one is only for demonstration of the materials aspect and the robotic aspect, and we consider the fact that this shouldn't be against the limitations that we have on the moon. We should select a space grade polymer, and everything else like outgassing requirements should be considered. But it's a very good next step as well. Yeah.
Makes sense.
Thank you very much.
Thank you, Mohammed.
Thank you.